All right, everybody. Hello, welcome back. Thanks so much for being here. We continue our journey in diving into our next topic here, groundwater. Groundwater is a really fun and interesting topic. We interact with groundwater all the time, whether you know it or not. It's in our water bottles. It's in our reservoirs in some cases. It is all around us, groundwater. For some of you, it may be news that there is water underground, and it is a vital resource that we have available for us there in that water below ground. One that we need to make sure that we protect and utilize in a sustainable way, and also one in which presents a lot of opportunities for people interested in pursuing geoscience as a career. And that is, there are a lot of jobs in topics surrounding groundwater, from groundwater contamination, groundwater resource availability, groundwater extraction. All of these things involve input from geologists, and that all started, the training of those geologists started right here in GEO1 in discussing groundwater. So our objectives for today are not to make you a licensed professional in groundwater, but rather to introduce you to these concepts and key terms related to groundwater, and hopefully show you how that applies or how these topics apply to your life in general. So we're going to define groundwater. We're going to talk about some terms related to how we describe what's called the aquifer. We're going to describe how groundwater moves. It moves. It does. It's absolutely cool the way that it moves in the subsurface there. And then we're going to describe the availability and significance of groundwater. There's a lot of groundwater out there, a lot of it. A lot of groundwater. In fact, it is the second most significant reservoir for fresh water on the planet, right after ice sheets and glaciers. There's a huge amount of water below the ground. However, the portion of that groundwater that we could actually use as drinking water, really small, right? Really, really small. That's number one. Number two is that groundwater takes a long time to be replaced. And this is an average rate of water exchange for water recharging in aquifers. It's going to take around 280 years or so. 280 years. We utilize groundwater much more quickly than that. Groundwater is a non-renewable resource. And that's because our use of this resource far exceeds the rate at which that resource can be replenished. So it is a non-renewable resource. Even despite there being so much of this stuff, it takes a long time to recharge those aquifers that we can use for things like our drinking water or for agriculture and those sorts of things. And so with that said, it is a non-renewable resource, and one that we need to make sure that we take good care of. And in this case, or for this class, that we also understand. And so, again, there is water below the ground. There is water in the ground. If you were to, say, go out to the park and be allowed to dig a hole there at the park, you would likely see in the upper layers of that hole, right near the top in your soil there, you would have those clay and silt minerals, or those clay and silt particles retaining some moisture there in the soil that's being utilized by the plants and all of that good stuff. But below that, in the sediments underneath that, you would see that things would get pretty dry, right? It would get pretty dry. And if you could take those loose sediments and zoom in on them with a microscope, right, you could see that in between, what you have there is a pile of sediments, and in between those little sediments, there are openings. And in those openings there, in that dry area, you would see mostly air, mostly gases, right? That's what you would mostly see in that zone there of those loose sediments. We call that zone the zone of aeration. That's the zone of aeration. This is also sometimes referred to as the vadose zone, V-A-D-O-S-E, the vadose zone. So the zone of aeration or the vadose zone. If you were to continue digging your hole, if you were to get really, really deep, however, eventually eventually you would cross what is called the water table. On the other side of the water table, below the water table, is the zone of saturation. The zone of saturation. In that zone of saturation, now all of those same openings are now filled, are saturated with water. And if you were to install a well in this zone, a groundwater well in this zone, you would see that that water would actually flow towards that well and would fill a portion of it that could be extracted and utilized, right? That is the zone of saturation. So we have this zone of aeration, and this zone of saturation is separated by the water table. And you might notice that just above the water table is this little thing called the capillary fringe, right? The capillary fringe. You may have one day been out having a bite to eat, and maybe you spilled a little bit of your drink, or maybe a little bit of moisture came off of your drink and ran on the table, and maybe that little bit of moisture happened to touch your napkin or maybe the sleeve of your shirt. And you notice that that water kind of gets slurped up by that fabric. It almost looks like it's motorized. It gets kind of pulled into that fabric, and it wicks into that fabric. That's because water is a special substance. It has a high surface tension. And what it's doing is it is filling all of those little openings in the napkin because of that high surface tension. So the water, it's running into that napkin, it's filling all the little tiny holes in that napkin, and eventually will stop, right? When that water runs out or whatever, it will stop. It won't continue to slurp up more water, right? Eventually it'll stop. Same thing's happening in the subsurface. Just above the water table, that water is wicking into those overlying sediments, running upwards into those overlying sediments. That's what we call the capillary fringe. That's the capillary fringe there, just above the water table. It's that little bit of water that wicks up into those overlying sediments. That's why you see that drawn in there. So some important terms in there: zone of aeration, zone of saturation, water table, capillary fringe. But also an important part of this graphic is that you notice that the water table that's drawn in the lower portion of this graphic, notice that the water table there, it's not flat. And in general, that water table seems to mimic in its shape the overlying topography, which is oftentimes true. The water table has a slope to it. It has a slope to it, or what's called a gradient, a hydraulic gradient, a hydraulic gradient. That is the slope, right, or the pressure differences between or at various portions of the aquifer or along that water table there. So in an aquifer that is open to the atmosphere and it's just present within a pretty homogeneous bit of sediments, generally that hydraulic gradient is going to flow from areas of high elevation to low elevation, just like a hill, right? Just like if you took a ball and you rolled it down a hill, that ball is going to roll downhill. If you take a drop of water and you put it in the higher elevation portions of the aquifer, it's going to flow downhill towards the lower portions of the aquifer. We're going to see when we talk about certain other types of aquifers, confined aquifers, and other conditions, that it's not always that it flows from uphill to downhill. But what is always true is that water will flow from its high pressure elevation to its low pressure elevation along what is called, the differences between those elevations, that's what we define as the hydraulic gradient. So if you install two wells into the aquifer and you measure the height of the water table in those two wells, and the water table is higher in one of those wells than it is in the other well, then that means that that water, its flow will be directed from that high elevation to that lower elevation. And so what commonly hydrogeologists are tasked with is determining the flow direction of groundwater by looking at the different pressure elevations, right? By looking at the hydraulic gradient, by measuring groundwater table elevation at many points. And so what you might do is you might go out and install a bunch of groundwater wells out there, right? A whole bunch of them, and then measuring the water table elevation in each well. So that's what's present in the top portion of this image right here, is a bunch of measured groundwater elevations here, right? So 138.47, 152.31. So obviously the height of the aquifer here is much higher than it is here. Once you go and you collect that data, then what you do is you contour that data. That is, you group and separate out points, right? Such that you're showing the slope of that water table, right? So along this 150 contour line here, this 150-foot contour line there, that's where this geologist estimated along that entire line that the height of the water table was at exactly 150 feet. Same for 140 and 130. And as we noted, that water will flow from that high pressure elevation to the low pressure elevation, right? So if we were to imagine dropping a drop of water right here along this dashed blue line, this is the path that that water would take. That's the direction that it would move along that gradient. And why is that important? Yeah, of course, Sappenfield, water rolls or flows downhill. Why is that important? It's really important because when we map out things like contaminated portions of the aquifer, this gives us an indication of where that contamination might have already went and where it might be going. What I mean by that is, let's imagine that you had a situation where you are a highly successful hydrogeologist and you are tasked with representing a client who operates a chemical manufacturing facility right here, right? Right up the road from your chemical manufacturing facility here is a school. There's a school full of young individuals that are particularly susceptible potentially to exposure to the contaminants that you utilize for your operations and or your client uses for their operations. And tragically, one day there is a spill at your facility. And representing that client, you're immediately concerned about this school and these individuals that are learning there, right? And you're concerned about whether or not they're going to be exposed to these chemicals. And so is your client, right? And so are the regulators that are aware of this spill as well. And they ask you, is there any reason for concern? Do we need to warn the school? Do we need to shut it down? And you would say, well, based on our mapping of hydraulic gradient, those contaminants should flow with groundwater in this direction. So this should not be of concern to this school. And everybody goes, whew, well, that's good news, right? Well, that's good news. And so again, it's not just the groundwater that's flowing, it's also those things that it's carrying, right? And so understanding hydraulic gradient and mapping it, again, is something that geologists will commonly be tasked with doing, okay? So hydraulic gradient certainly influences the way that water moves, but there are other influences as well, namely the nature of the material that holds the water. We learned when we talked about sediments and sedimentary rocks and those sorts of things that there are different sediments with different sizes and different shapes, and those different sizes and shapes of sediments, they come together to yield materials that have water stored and moving within it very, very differently from one another. All right. So we have to describe the nature of the hydraulic properties, right? The way that water moves through these various materials. And the first thing that we want to note maybe is what's called porosity. That is, if you have a block of sediment, if you have your block of materials, you might want to know, well, how much of that material has those little openings that are capable of holding water? That's what's called porosity, and that's typically given as a percentage of volume of rock or rock. right? So if you have a volume of rock, right? A volume of rock, the percentage of that rock that is open space, that's what you're going to describe as porosity. Certain sediments, certain rocks may have high porosity, but those pores might actually be disconnected from one another, or they all might be connected to one another. The connectedness of those pores influences what's called permeability, which is the ability of a material to transport fluid, right? The ability of a material to transport fluid. So if you had, let's say you took 100 gallons of water and you filled up a bunch of water balloons with that 100 gallons of water, right? That 100 gallons of water, you put them in those water balloons, you put those water balloons right next to each other on the ground. There's 100 gallons of water there, but they're all contained within individual water balloons. And so there's no connectedness there. There's no permeability between the water balloons, right? Whereas if you have a pipe and you put 100 gallons into that pipe, that water will flow and transmit itself freely through that open and connected pipe, which has then a high permeability, right? So different sediments, different materials will have varying levels of porosity and permeability. Some materials have high porosity, low permeability. Some have low porosity, relatively high permeability. And so in thinking about the aquifer and thinking about, extracting groundwater, what might be more beneficial, right? If something has high porosity but low permeability, that's not really a good aquifer material, right? Because even though there's lots of openings in there that might contain water, that water's not going to move, right? The water's not going to move. You could put a bucket in and among those water balloons, right? And no water is going to get inside of that bucket. However, if you have a pipe and you put that bucket at the end of the pipe, all that water is going to flow into the bucket, right? Higher permeability seems to matter there in the quality of the zone of saturation. Two other really important terms here then related to porosity and permeability are aquitard and aquifer. So low permeability layers, right? Layers that do not transmit fluids. They serve as a barrier to groundwater movement. That can be lateral groundwater movement or vertical groundwater movement. That's what we call an aquitard. And these are going to be generally low permeability materials. An aquifer is a rock or a layer of sediment that transmits that groundwater freely. Water moves freely through the aquifer. So this is what you're going to want to tap into for your groundwater supplies. And in looking at various materials, we can look at these properties at porosity and permeability related factors to determine which materials are going to make the best aquitards and which materials are going to make the best aquifers. So listed here are various sediment and rock types with their corresponding porosities. So we can see that clay has a high porosity. If you were to look at a block of clay under a microscope, you'd see a lot of that block of clay is open space between those individual kind of platy shaped clay mineral grains. A lot of open space, a lot of porosity. Sand, also a lot of open space, a lot of porosity. Same with gravel, same with limestone, a little bit less with sandstone and basalt. Granite, the porosity is very low. It's really low. There's not much open space at all in granite because intrusive igneous rock, all those mineral grains form that interlocking network. There's not a lot of open space in there, right? So granite, with its low porosity, probably not going to have much water there. We can kind of rule that out as a good aquifer, right? Some of these other rocks, though, may be worth exploring. But to know, again, whether it's going to be a good aquifer, we need to look at its permeability. And the permeability of these materials is summarized on this table by describing what are called the specific yield and the specific retention. The specific yield of these materials describes the percentage of water within that pore space that would flow freely due to gravity. So what I mean by that is you've got that block of clay that contains 50% porosity. 50% of that block of clay are little open spaces within it. If that material was fully saturated, right, only 2% of the water in those openings would move due to gravity. Only 2%. The remaining 48% would stay right where it is. And those little, our analogy there, those water balloons, right, just sitting there by itself. So specific yield, notice that specific yield and specific retention, if you add those values up, they add up to the porosity value provided, right? Because that's saying that 2% of the volume of the rock, right? That saturated volume of material, only 2% of that water is going to move. That specific yield, 48% is left behind. So obviously those numbers need to add up to account for that total porosity, right? And so again, specific yield and specific retention are ways of describing the permeability of these materials. General rule of thumb, a low specific yield speaks to a low permeability of these materials. So whereas clay has all of this open space, notice that its specific yield is very low. You're not going to get much water out of that material. The water is not going to move in that clay. Whereas in our sand, while the porosity value is lower, notice that the specific yield value is very high. So that water is going to move, right? So what that means, right? Again, low specific yield, low permeability, high specific yield, higher permeability, right? What that ultimately means is that a good aquitard is typically something that has lots of clay in it, lots of clay. And these aquitards are very important in that they impede groundwater movement, but they also impede, say, the movement of contaminants in the subsurface. A lot of our aquifers are protected in some cases by multiple aquitards, which prevent surface contamination from moving down into the aquifer and introducing those contaminants that can make sick. Right? So mostly clay-rich materials are going to be our good aquitards, whereas our good aquifers, those things that we're actually going to be extracting groundwater from, are largely going to be sandy or sand-rich materials or gravel-rich materials, those sorts of things, again, with the higher permeability. All right. Another important term or another important concept regarding aquifers is the water is replenished in an aquifer. Precipitation here at Earth's surface, other surface water sources, they percolate water into the ground and they introduce new water into the aquifer. We call this process, we call it recharging the aquifer. When we put new water into the aquifer, we recharge it. And the amount of time that it takes to recharge an aquifer really depends on the area over which that recharge occurs. This is a big deal here recently because, or here in California, because we rely so much on the aquifer, and also our state has been so heavily developed, and a lot of that development has included the development or the inclusion of impervious surfaces, things like parking lots, building foundations, right? These surfaces where water can't make its way into the ground, which takes the size of the recharge area and it shrinks it down, which means that our aquifers that we rely on and already are a non-renewable resource, it makes them recharge even more slowly. So interestingly, there's been a push and absolutely permitting requirements that in some new construction, they include areas where the groundwater can infiltrate the surface. So you might see in certain parking lots, instead of having an asphalt parking lot, you might see the use of pavers that have little openings. There's also new asphalts that are designed with holes in them that allow the water to get in, and that's what they're doing, is they're trying to increase the size of the recharge area for the underlying aquifer so that we can get that aquifer recharged as fast as we possibly can. All right. All right. So we also have multiple types of aquifers, and the type of aquifer depends on the distribution of those aquifer and aquitard materials in relation to the zone of saturation and the zone of aeration. These are our three main aquifer types, so you might want to list these in your notes with a little bit of space, because we're going to provide you with the definitions for each of these: unconfined, confined, and perched aquifers. All right, so here we've got this terrain. There's groundwater in the ground there, and what we have here first off is the main aquifer there is an unconfined aquifer. That is this zone of saturation down here, right? That aquifer is unconfined. It does not have on top of it an aquitard. It is open to the Earth's surface. That means that any water that falls on the Earth's surface and starts to make its way into the ground can make its way down into this unconfined aquifer, right? Above the unconfined aquifer, sometimes you'll have layers of fine-grained sediments, right? Maybe these are layers of sediments that were deposited millions of years ago that are now buried by more sediments, but these fine-grained layers or these impermeable layers, those are, again, great aquitards. And what they will do is they'll intercept some of the water that would otherwise be moving its way down into the zone of saturation. And that water starts to collect on top of that aquitard material and form what's called a perched aquifer. A perched aquifer. So a perched aquifer is a saturated zone within the zone of aeration, right? That's typically caused by, again, one of these aquitard layers being present within that zone of aeration. All right. Our last type of aquifer is what's called a confined aquifer. So as you've noticed in this class, and maybe just in your journeys around, that we oftentimes see layers of sediment, or we see layers of sediment preserved in the rock record. And those layers might alternate in what they're made of. You might have alternating layers of gravel, of sand, of clay, right? And you might see those patterns repeated over and over and over again. Those layers of clay are going to make great aquitards, and those layers of sand and gravel and things are going to make great aquifers. And so those layers in and around, say, a mountain may be contorted, right? Deformed by that tectonic activity, as we're seeing in this image here, the principle of original horizontality, right? Calling back to our talk about geologic time and Nick Steno, that principle of original horizontality is preserved out here in these portions of the aquifer, but tectonics took these portions of these layers and kind of bent them up such that these sandy layers, this aquifer material, is exposed here in this mountain range. Being exposed at our surface means that water can move into that aquifer. Water that otherwise wouldn't enter that aquifer because it's overlain by a aquitard, right? So water falling out here over this valley might try to make its way down into the aquifer, but it never succeeds because you've got this aquitard there in the way, preventing that water from moving down into the aquifer. Underlying this aquifer, we see another aquitard, right? And so this aquifer is confined, and that presents a really unique condition in that in this situation, what we end up doing is once we fill that aquifer, right? Once we've put water in that aquifer and start to bring it to these higher elevations, we provide it with some pressure. Now that water is pressurized, the same as if you filled a hose with water, right? If you take a hose and you fill it with water and you hold both ends of that hose at the same elevation, right? The water is going to rise to the same elevation in that hose. If you take your thumbs and you place it over either end of that hose, you can take one end of that hose and hold it very high. And when you do that, you put some potential energy in that water, such that if you take your thumbs and then suddenly release them, water is going to flow out of that lower point on the hose. In groundwater terms, this is what we call an artesian condition. This is an artesian condition. So if we came up here in the mountains and drilled through the aquitard into the aquifer, we would see that once that pipe penetrates the aquifer, water would rise in that pipe to an elevation higher than we had encountered it during our drilling, right? It would rise up to the elevation that's at the top of that saturated portion of the aquifer, right? Do you see that? That's what's going on there, right? We've got the pressure surface here, right? Pressure surface here. So water would rise up to that point. It wouldn't flow out of the well, but it would rise in that pipe. Anytime that you get water, when you put that pipe in the ground and the water rises to an elevation higher than where you first encountered that water, that's what we call an artesian condition, right? And because water's not flowing out of this well, we more specifically call this a non-flowing artesian well, right? And that's because the well's top extends, again, above that pressure surface. If we go out into the valley, however, and install a well, now we can install the top of that well at an elevation below the pressure surface. And when that happens, what we get is something called a flowing artesian well. And this is what that looks like. This is water will come right out of the ground in this flowing condition without any motors required, any pumping required. Simply install the pipe into the ground. And as long as that pressure surface stays above the aquifer, that is, as long as the rate of recharge here exceeds the rate of discharge here, that pressure surface will stay above that the top of that well casing, right? So we get a flowing artesian well. We're using gravity to get this water out of the ground. And these flowing artesian wells, obviously very popular in that no energy required. Gravity's doing the work for you. You can get this water to the surface and then utilize it. The problem is that these things will only flow for so long until all of that water is then depleted. This pressure surface will drop and drop and drop and drop and drop. And once it falls below the top of this well, no more flowing condition. And now you got to install pumps and all that other kind of stuff, right? Another great example of or analogy for an artesian well is one of these things. I've read about these things. Not exactly sure what's going on here, but from what I read, this is something referred to as a beer bong. And what you do here with this device, evidently, is you take the beverage and you pour it into this tubing here, right? You take that tubing and you fill that with your beverage. And then reportedly what you do is when you're not ready to consume the beverage, you make sure you hold this pipe above the elevation there of the beverage in the tubing, and then it won't flow. But the second you take that tubing and you drop its elevation, you lower it, that beverage comes out and comes out really rapidly. It's exactly how an artesian well is operating, is that with that water held at this height via recharge, when you have that pipe now down in the valley there at a lower elevation below that pressure surface, that water flows. It's the exact same thing. All right. Awesome. So you can entertain everybody at parties with descriptions of this. Certainly, they will be enthralled, no doubt. Okay, a little bit of doubt, but I would be entertained by your discussion. I think it's cool. All right. So groundwater's movement has a huge impact on the subsurface. One of the things it does, and one of the things that we've talked about already in discussing weathering and erosion, is talked about how groundwater dissolves rocks. Groundwater is mildly acidic. It contains a really weak carbonic acid, but it's enough, right? It's enough That carbonic acid is sourced by rain dissolving carbon dioxide, also from decaying plants. But that change in pH is enough to actually start to dissolve then calcite and limestone. And when it does that, right, it leaves big openings. It leaves big openings or caves. These caves, speleothems, as they're sometimes referred to, again, are dissolved bits of calcium carbonate. This is Carlsbad Caverns. These dissolved openings in a bit of limestone caused by the movement of groundwater. These caves will sometimes have in them long spiky objects, either extending from the ceiling or extending from the ground there. The spiky things that hang from the ceiling, we call those stalactites. Those that come off the ground, we call those stalagmites. You can remember the stalag has a G in it, like the ground, and stalac has a C in it, like the ceiling. So that's one way to remember which is which is a pretty common thing to get those mixed up. But that's one way. But really importantly, these little spiky things can actually be evaluated for their chemistry, which has a direct correlation with chemistry going on in the overlying atmosphere and groundwater and those sorts of things. Because again, that carbonic acid that the groundwater is moving and carrying is produced by decaying vegetation and carbon dioxide and those same things that influence atmosphere or that are present in our atmosphere's chemistry here at the surface. So these things are analyzed all the time for climate reconstructions and all kinds of really interesting things. They're also analyzed for where these caves occur, because karsting, as we described when we talked about weathering and erosion, can produce some pretty dramatic landscapes with these caves as they collapse and cave in, sometimes do so in inconvenient places. Again, the dissolution of these things doesn't know really what's going on above it. And so when these caves open up and form very close to the Earth's surface, the structural integrity of that surface is weakened quite a bit and can cave in these sorts of sinkholes. Another time that, or another example of groundwater interacting with the surface is at hot springs. Hot springs are simply hot groundwater. That's it. When groundwater comes out of the ground, we call that a spring. When it's hot, we call it a hot spring. And so these hot springs, they generally form around areas where there is a heat source. That is around active plate tectonic boundaries or areas where there is active volcanism. That is, you have a heat source very near the Earth's surface, and that heat source then takes that water and heats it up, right? That water loses some density and rises to the surface. Hot springs are relatively common here in California. There's a number of them. There's a number of hot springs up near the Mammoth Lakes area. You can see them, you can visit them, some great viewing of hot springs that we do on some of our field trips. Those are caused by a heat source that continues below what was the Long Valley caldera, which we discussed when we talked about volcanoes in this class. But that heat source is still there. Water moves across it and then runs into a series of faults in the area where that groundwater runs along those faults, comes out at the surface, and is really heated. It's also loaded with minerals, and so makes some really beautiful mineral deposits at the surface. And so this is a distribution of some of the hot springs found here in the United States or in the lower 48 here. Again, many of those found here in California. All right. So let's talk about some of the problems associated with groundwater use. Okay, let's talk about some of the problems associated with groundwater use. The main one of those being that water is a non-renewable resource. We utilize groundwater for a whole bundle of things, from drinking water to agriculture. Groundwater is a vital resource. And that has a lot, especially here in California, that has a lot to do with the variability of our state's climate, along with the population that lives here, along with the importance of the agricultural industry that exists here. California can experience years of feast and years of famine as it comes to precipitation. We have years where we get lots of rain and all of our reservoirs are filled up and we are good to go. But then we have also some periods where drought can persist for years and we utilize those surface water resources to the point that we essentially run out or nearly run out. In those times when precipitation levels are low and direct rainfall on our crops or import of those surface water resources is limited, where we oftentimes turn is to groundwater. And we need to grow these crops independent of what the precipitation pattern is for that given year. Those crops need to be fed water. And so if there's no rain falling on those crops, we need to find that water somewhere. And oftentimes we turn to underground to do so. And a lot of times these aquifers that we tap into for that clean, fresh water to be able to do this activity, right? That water is very old. It takes a long time to recharge, much, much longer amount of time than it takes for us to use it. So that non-renewability of this resource is a big deal. When we utilize this resource, when we take groundwater out of the ground, one of the things that happens as you pull water out of the ground, as you remove that water from the pore space, what the aquifer will actually do is it collapses a little bit. With that water missing from the subsurface, the aquifer will collapse a little bit. And when you take out thousands upon thousands of gallons of water, that little bit of collapse can add up to a lot of bit of collapse. And that manifests itself out right here at Earth's surface in the form of subsidence. That is a lowering of the Earth's surface at these places. And these are some dramatic pictures. This picture here on the right is a really famous image from the San Joaquin Valley showing subsidence from 1925 to 1977. That is, at the time this picture was taken in 1977, the ground elevation in 1925 was at approximately that point on that telephone pole. In a little more than 50 years, because of aquifer use, that's how much the ground has dropped in elevation. That's how much the height of that from that 1925 to that 1977, that's how much that shows the distance that the ground has subsided through that amount of time. Here's a more recent picture put together from the USGS showing subsidence from 1988 to 2013. So a little bit taller than this person, the ground has dropped in that amount of time. So lowering elevation is a big deal because what that will start to do is that'll start to take some of the infrastructure that you have installed at the surface, things like aqueducts, roads, bridges, and those things will start to fail and need repair, really expensive repair, really, really costly repair. The other thing it does, once that aquifer collapses that little bit, that collapsed space is never available again for water storage. That storage space for the aquifer is lost forever. You can't get it back. The earth does not reinflate itself. This is permanent, this subsidence. This is absolutely permanent. You can't get it back. So this is sort of this is lost space, right? Which is most certainly a concern as well. So subsidence related to aquifer usage is a big, big deal. Another issue that you can face in groundwater use is intrusion of those bits of water that you don't want in your well. Let's say that you wanted to tap into the aquifer near the coast, right? So you install a well. When you install that well and you start to pump on it, you start to pull water from all directions towards that well. And if you're close to the ocean, salt water is also present in the ground. Salt water is a little bit more dense than fresh water. So normally that fresh water kind of sits and floats on top of that ground, of that salty groundwater. However, if you start to pump on that well, what you can get is that salt water will actually move its way up into the freshwater portions of the aquifer and start to mix. right? And actually will take that well that you've been pumping on, you'll end up starting to pump salt water if you're pumping on that material too hard, right? And so, again, that's a big issue because once you do that, it's really hard to reverse course. So saltwater intrusion is actually a really big deal here locally in Southern California. And if you go to Orange County, they actually have wells installed where fresh water is injected into the ground as a sort of wall or hydraulic barrier for saltwater intrusion to help protect their aquifer. That is, they have a bunch of pipes installed along the ground near the coast. They pump water into those wells down into the ground to act almost like a wall or a curtain that keeps some of that saltwater intrusion from moving far inland where some groundwater production wells may be, or some portions of the aquifer that they want to protect may be. All right. It's another issue to consider with using groundwater. Groundwater contamination is another really big one. Again, because groundwater moves, that means that impacts to the aquifer in one place most certainly can and will impact portions of the aquifer that can be very far away. So let's imagine that you've got yourself an aquifer and you've installed your well into that aquifer and you're using that aquifer, and all of a sudden you notice that your water is dirty. That through testing, you can see that there's been something that's making your water dirty. And you map that out and you find out, well, it's because my neighbor's septic system that they have is leaking. And those contaminants from that septic system, they leak into that water, right? And then those leak contaminants, they migrate then to that nearby groundwater well that we're using, right? So again, because of the movement of groundwater, things that you might not even know are happening can have significant impacts on your supply. And so what this requires is that you do regular testing and monitoring of your groundwater supply to make sure that everything is safe and not contaminated. Because some of these contaminants can show up in such small quantities. We're talking parts per billion and still be considered toxic, right? So certainly something that requires regular monitoring. Also, we might have situations where, again, somebody else's activities end up impacting our wells. That is, let's imagine we've got ourselves, we have our septic system, but we knew the hydraulic gradient from our septic system should have sent any potential leaks away from our property, say to the west. So we go ahead and we install our groundwater monitoring well up gradient of that location to the east, thinking, well, if there is any leak from our septic system, it's going to go the other way, right? So you install your groundwater monitoring well or your groundwater well, and all is good. That is until a farmer nearby goes ahead and installs a groundwater well that he's going to use for his irrigation. So they install that well and they start pumping on it really heavily. And by doing that, they effectively reshape the water table. They reshape the aquifer such that the hydraulic gradient ends up reversing. That's what you're seeing in this image here, is that the hydraulic gradient has completely reversed, which is sending any contamination from that septic tank now into your what was an upgradient well. So again, this use that's external to you of the water table, right, is most certainly something that can have an impact on you and your activities. Agricultural runoff, right? Agricultural runoff or infiltration of contaminants from things utilized for agriculture, which are great for maybe controlling pests or making our crops grow. They absolutely cannot be good in drinking water. Similarly, contamination, say, from landfill runoff, right? That is chemicals that might be that might have put in the landfill, or chemicals that we're just disposing of regularly or utilizing as part of what we do. Those absolutely can end up in the aquifer as well. And contamination of the aquifer is exceedingly expensive. Installation of these wells that we've talked about so far can cost tens of thousands, if not hundreds of thousands of dollars to put into the ground. Contamination of the aquifer then can render these things effectively useless. Investigating the aquifer to see where contamination might have went, figuring out ways in which to treat then the aquifer to make that contamination inert. All of these things require enormous amounts of money, oftentimes millions and millions of dollars to treat the release of what we normally think is maybe a relatively small amount of contaminants. So it really can be costly. And if you guessed that that's something that a geologist might be involved in, is investigating where this contamination is, what was its source, where is it going, who's potentially impacted, how much contamination is there, how do we treat it? If you guessed that, you absolutely guessed right. And in fact, that's what a lot of people that get into the field of geology do, is they go out and they address these sorts of issues. They look at this contamination, they look at the types of sediments, the nature of the aquifer, the presence or absence of any aquatards, and all of that kind of stuff to describe a site, to describe where these materials might be found, and describe those ways in which we might be able to treat or remediate those materials. It's really, really important. It's something that, again, impacts our lives every day. Once again, aquifer usage is something that is really, really something that we need to do, particularly here in California, where precipitation patterns can be so irregular, right? A couple big aquifers here. The Ogallala aquifer, 27% of irrigated land in the U.S. is supplied by this aquifer. We have extracted around 10% or so of the volume of water in that Ogallala aquifer. And the rate of recharge for this aquifer, around 6,000 years. So if we just stopped using the aquifer today to get that 10% back, that's going to take about 6,000 years for that volume of water to be replaced. So again, a non-renewable resource. Here, more locally in California, a lot of our groundwater is extracted from what's called the San Joaquin Valley, where 7 million acres of crops are irrigated, in part using this groundwater. This aquifer is composed of mostly just a thick accumulation of continental sediments. And one of the big ticket items, as we saw in those previous images, the problems that are being experienced in this area has to do with rapid subsidence. That is the land surface subsiding and then resulting in damage to civil infrastructure, loss of aquifer space. This has been so significant in the state of California that recently there's been a new bit of legislation introduced. And this is certainly something that you want to have in your notes. That is the Sustainable Groundwater Management Act, otherwise known as SGMA, SGMA. The Sustainable Groundwater Management Act was recently signed into legislation requiring that the state figure out a way to sustainably use its groundwater supply. SGMA specifies that the state's aquifer network is broken into a series of provinces or groundwater basins. The aquifer is partitioned in that way, and then each basin is provided or has a defined bit of local oversight. That can be oversight from local regulators or local political leaders, right? These people all have control over their little part of the aquifer. What SGMA is requiring those groups to do, those groups are called groundwater sustainability agencies, which again oversee each of these little portions of the aquifer. What those groundwater sustainability agencies are being tasked with doing is developing plans for how they are going to make their use of their portion of the aquifer sustainable. These plans are called groundwater sustainability plans, or GSPs, and what they're going to include is groundwater models, usage characteristics, a whole bundle of things where the amount of groundwater that's being utilized has to match the amount of water that's being put back into the aquifer. This is going to have, Sigma is going to have a huge impact on all of our lives here in California. That is all of those groups, organizations, businesses that utilize water in what they do are going to have to get more efficient at utilizing that water. We're talking mines, we're talking landfills, we're talking manufacturing facilities, we're talking about residents. All of these groups are going to need to get better at reducing the amount of groundwater that they rely on. And then there's going to have to be a whole bunch of technology that's installed that's going to have to continually help us to continually grow in our understanding of our state's aquifers and continually grow in our efforts to help the aquifer to recharge more quickly. There are so many opportunities in Sigma. Beyond what this implies for us being here in California, in terms of jobs within this field, Sigma is going to have a huge impact. The task of modeling the state's entire aquifer system is monumental. The tasks associated with making these processes more efficient, the tasks associated with getting this water out of the ground and putting water back in, all of those things are going to require input from geologists, and it's going to be a remarkable bit of work that comes out of all of this. I'm looking forward to seeing how this goes and continuing to watch how this goes. And if you're interested, as always, in hearing more about Sigma and opportunities that may lie out there for groundwater related efforts, that's what I'm here for. I'm more than happy to talk about it. I spend a lot of my time working in the private sector in groundwater related issues. It's absolutely fascinating. I'm more than happy to talk about and share my experience. So again, you're always more than welcome to reach out and chat with me about it. All right. So in summary, groundwater is important, right? And there's a lot of it for now, right? There's a lot of it for now. It's a non-renewable resource. And so groundwater movement, remember those terms: zone of aeration, zone of saturation, capillary fringe, porosity, permeability, and how these terms ultimately dictate groundwater movement with this interplay between gravity and geological conditions, right? And ultimately, it's a resource that we really need to utilize sustainably, right? Because it is a non-renewable resource, but it's an important resource for maintaining our standard of living. All right. So with that, that concludes our discussion. It's always fun to talk groundwater. And as always, you are more than welcome to reach out to me anytime. I'd be more than happy to chat with you about any of this, provide any clarification that I can that would be helpful. And with that said, I'm going to wish you all a wonderful day. Please be safe out there. Take care of yourselves, and we will talk again very soon. All right, everybody, take care.